Hello guys, today we'll be looking at Poisson distribution, which is also one of the discrete probability distribution that we have. So in Poisson distribution, Poisson distribution involves what? The number of occurrence of an event within a specified time interval. So let a random variable x, a random variable x be the number of occurrence of an event. Let a random variable x be the number of occurrence of an event within a specified time interval. Let a random variable x be a number of occurrence of an event within a specified time interval. Then x is said to follow a Poisson distribution with parameter lambda if the probability of x equal to small x is equals to lambda raised to power x exponential minus lambda all over x factorial, where x is equal to 0, 1, 2 till infinity. So what does say? That if this random variable is the number of occurrence of an event within a specified time interval, then x is said to follow a Poisson distribution with parameter lambda. This lambda is called the mean rate of occurrence of an event. So it's said to follow a Poisson distribution with the parameter lambda if the probability of x equal to this, which is the probability mass function, is given as lambda raised to power x exponential minus lambda all over x factorial. Okay, so we'll be looking at what? The expectation, variance, and the moment generating function of a Poisson distribution. So, and we're going to start with the expectation of x. The expectation, comma, variance, and the moment generating function of a Poisson distribution are lambda exponential lambda exponential t minus 1 respectively. So the expectation, variance, and the moment generating function of a Poisson distribution are lambda, exponential lambda bracket exponential t minus 1 respectively. So we'll be proving how the expectation of a Poisson distribution is equal to lambda, how its variance is equal to lambda, and how its moment generating function is equals to this. So let's start with the expectation of the random variable of a Poisson distribution. Earlier before now, we defined our expectation of a discrete random variable to be what? The expected value of x a lot before now we find our expected value of x of a discrete random variable to be equal to summation as x equal to 0 to infinity of what x probability of x equal to what x. But we have that the probability mass function of a Poisson distribution to be what? Probability of x equal to small x to be lambda raised to power x exponential minus lambda all over what? X factorial. Okay? So putting this inside this, we have that the expected value of x is equal to summation as x equal to 0 to infinity of x lambda raised to power x exponential minus lambda all over x factorial. So expanding this, we have that the expected value of x is equal to summation as x equal to 0 to infinity of x lambda raised to power x minus 1 exponential minus lambda all over what? X minus 1 factorial. So lambda raised to power x is the same thing as what? Lambda multiplied by what? Lambda raised to power x minus 1. So by doing this, I have not committed any error by saying that this is equals to what? This. So what will it, what's the next thing? This x, we have to cancel this x, and we have lambda and exponential minus x, which is what? A constant that needs to what? To be separated from what? The summation. So this will give us, this is equals to lambda exponential minus lambda summation as x run from what? 0 to infinity, as x run from 0 to infinity of what? Lambda raised to power x minus 1 all over what? X minus 1 factorial. But in mathematics, in series in mathematics, we have that when you are summing, when you are summing over the range of what? A certain variable, when you are summing over the range of a certain variable all over each what? Factorial, this will give you, for instance, if you have summation, if you have exponential, or if you are summing in mathematics, you know that if you are taking the summation of a certain parameter as a certain variable raised to the power of another variable all over that variable factorial, will give you exponential of this. So this will give us, if you apply that here, you have that this, a whole of this will give you exponential what? Lambda. So multiplying this, we have that lambda exponential minus lambda multiplied by what? Lambda raised to power what? Multiplied by exponential lambda. So this we cancel out. So we have that, we have only exponential, we have only lambda left. So this implies that expected value of x of a Poisson distribution is equals to what? Lambda, which is the mean rate of occurrence. So let's look at each variance. You know that variance of x is equals to expected value of x squared minus expected value of x all squared. So variance of x is equal to expected value of x squared minus expected value of x all squared. So we will first of all get what? The expected value of x squared. We know that what? X squared, expected value of x squared is equal to expected value of x bracket x minus 1 plus expected value of what? X. We have already solved for expected value of x, so we'll first of all now solve for the expected value of x bracket x minus 1. Okay, so expected value of x bracket x minus 1 is equal to what? Summation as x run from 0 to infinity, as x run from 0 to infinity of x bracket x minus 1 lambda raised to power x exponential minus lambda all over what? X factorial. This is because we are dealing with what? Poisson distribution. So we have to expand what? This. So expand this, we have that this will give us summation equal to summation as x equal to 0 to infinity of x bracket x minus 1 lambda squared lambda raised to power x minus 2 exponential minus lambda all over x bracket x minus 1 x minus 2 factorial. So this, we cancel this, and we have this and this to be what? A constant. We bring it out of the summation. So this will give us this equal to lambda squared exponential minus lambda summation as x run from 0 to infinity, as x run from 0 to infinity of lambda raised to power x minus 2 exponent minus 2 all over what? X minus 2 factorial. And I have earlier told you that if you are taking the summation of something raised to power this all over that power factorial, will give you the exponential of this. So this will give us this implies that this is an implication sign. This implies that expected value of x bracket x minus 1 is equals to lambda squared exponential minus lambda. But we are solving for the variance of x, and the variance of x is equal to expected value of x squared minus expected value of x all squared. So this implies that variance of x is equals to expected value of x squared, which is lambda squared exponential minus lambda. This implies that expected value of x bracket x minus 1 is equals to lambda squared exponential minus lambda, and this is equals to exponential lambda. This will cancel this, so you have lambda squared. So the expected value of this is equals to lambda squared, and our variance of x is equals to expected value of x squared minus expected value of x all squared. So and our expected value of x squared is equal to what? This lambda squared plus expected value of x minus expected value of x all squared. So this will cancel this. We now have implies that variance of x is equals to lambda. Okay, proved. So let's solve for the moment generating function of a Poisson distribution. The moment generating function of a Poisson distribution. So in our previous class, I told you that the MGF, which is the moment generating function, is defined or is represented as mx of t, which is defined as expected value of exponential tx, where this t is what? A real number, So for a Poisson distribution, expected value of exponential tx is equals to expected value of exponential tx is equals to summation as x run from 0 to infinity of exponential tx multiplied by the probability mass function, which is lambda raised to power x exponential minus lambda all over what? X factorial. So x and lambda and exponential t have x in common. So bringing them together, you have that this is equal to summation as x equal to 0 to infinity of lambda exponential t raised to power x exponential minus lambda all over x factorial. So bringing this out, you have that exponential minus lambda summation as x equal to 0 to infinity of lambda exponential t raised to power x all over what? X factorial. I said before that when in mathematics, when you are summing over a something raised to power a variable all over that variable factorial, you simply take the exponential of the base, which is this implies that this, a whole of this, is equal to exponential. The whole of this is equal to exponential lambda exponential t. So this implies that the mgf, which is mx of t, is equal to exponential minus lambda multiplied by exponential lambda exponential t. So they have the same base. So you take one base and add their powers, which will give you exponential lambda exponential t minus what? Lambda. So what will you do? You take what? They have lambda in common, so you bring one out. Exponential lambda bracket exponential t minus 1. So this is what? The moment generating function of a Poisson distribution. Thank you. In our next class, we'll be solving a real life examples where you can apply a Poisson distribution. Thank you.